In 2024, the Fairbanks Museum and Planetarium hired Megan Duncan as its first female meteorologist and newest contributor to the Eye on the Sky program. Megan studied atmospheric and water resources science at Oregon State University and has a Bachelor of Science in Meteorology from Plymouth State University. We are so pleased to be collaborating with the Fairbanks Museum and welcome Megan Duncan.
Thank you very much for the kind introduction. I'm here today from the Fairbanks Museum. We're going to talk a little bit. Do you want to talk louder? Does that help? Or can we turn this up?
I can turn it up. Or you I'll turn it up.
And today we're going to be looking at some of the data that the Fairbanks Museum has collected since 1894 that I have had the pleasure to analyze and look at, talk about how our climate is changing, and maybe what we have to look forward to the future here in Vermont. If you have any questions, please write them down or however you want to take hold of them, and then we'll get to questions at the end. All right. So first, I want to start a little bit about me, since I am new to Vermont, give you a sense of where I come from and why I'm studying weather and why I'm here today.
What we're looking at right now, that's that tornado that's on the ground right now in Hampden County, moving east at around 30 miles an hour?
40 miles per hour.
40 miles per hour.
So if you live east of downtown Springfield, you got to be ready to get inside now. Take your family, take your pets with you. Bottom, innermost room of your home, preferably without windows. If not, head into the basement if you have one. If you're in a car, abandon it for a shelter. If you're in a mobile home.
So this was back in 2011. I was 12 or 13 years old in Massachusetts, where I grew up. And we had an EF3 tornado go through my hometown. And this is right at the prime age of trying to figure out what I wanted to study and what I wanted to be when I grew up. And this was definitely a big foundation to why I study weather. It actually missed my grandfather's house and hit his neighbors, and we were very lucky in that way. But it definitely sparked some interest in me in getting to see those funnel clouds and actually being outside playing soccer for a soccer tournament as a tornado was passing by just a few miles away. So I got to see the whole thing develop, and that really sparked a big interest in me. And so I was really interested about like why this had happened, how did it happen? Like in Massachusetts, a tornado destroying two-story homes is not very, doesn't happen very often. You don't really hear about it. And then I was thinking about, well, what about other tornadoes? How do those happen? And then soon after, I was just asking, how can I learn more, picking up everything that I could. And that's what led me to study meteorology. And I searched up schools, and one school that really captured my heart was Plymouth State, and that is in northern New Hampshire. It also helped foster my love of northern mountains, especially the Green Mountains and White Mountains. But while I was there, I had the opportunity to learn a lot more. And during my time, I found out that flash floods are actually the most dangerous type of weather. So that moved me from tornadoes to flash floods. And so I went to my professor and asked him, is there opportunities to learn about this? What can I do? And so I had the opportunity to go for an internship my freshman year, and I got to learn all about extreme precipitation, so how the water in the atmosphere leads to really heavy rain. And I'm lucky to be one of the few East Coast experts that study things called atmospheric rivers and extreme precipitation, and that led to quite a few different publications that I'm still very proud of to have been part of today. And so this led me to think of, okay, well, what's happening with the rain? How can we keep people safe? Since clearly the extreme precipitation isn't going away. I ended up graduating during the pandemic, as you can see up in the right-hand side. And while I was at school, I also got to do some broadcasting on TV for a hot minute, which led me to be interested in communication as well. And then that led me to, well, how can I learn more? So then I decided to move all the way across the country to a place I'd never been before, to the state of Oregon, where I went to Oregon State University. And this is where I decided to find out, well, I know what happens to the water in the air. Well, what happens when it reaches the ground? Where does it go? Why do we get flooding? So it allowed me to complete the full picture of the cycle of water, which was a great opportunity to have. I did a lot of outdoor experiences. You can see me doing some measurement of rivers here, where I got to analyze the flow and how to prevent flooding at these locations, which was a great opportunity. And it helped me learn a lot about why does it flood. At that same time, I got to work for the United States government for about 3 years, where I was a hydrologist estimating river flows and helping to keep people safe, as well as generating electricities on these giant hydropower dams out on the West Coast, which was a really interesting job. I even got to be interviewed for part of CNN, which referenced some of my articles when a big storm ended up passing through. So lots of great opportunities, but led me to still thinking about flooding. How do we keep people safe? And after spending a lot of time on the West Coast, I felt like I wanted to go back to my roots and move back east, and I wanted to learn a bit more. I felt like I had finished my time out there. I had learned everything that I could. Where to go next. So then I packed up and moved myself all the way back across the country with my loving husband, who reluctantly agreed to move all the way back to Vermont, back to my mountains that I loved, and ended up getting a job here, which I'm super excited to be here, especially to be in Steve Molesky's footsteps, following his footsteps. He was an amazing meteorologist here, and to take his place as he retired. Of course, here's the eclipse of 2024. This is my first week on the job. I need to see everybody come together, and I actually got to take meteorological measurements during that eclipse to help further an eclipse science project that Plymouth State was actually doing. So I got to be a part of that. And of course, shameless plug, got married in the White Mountains, and that was lovely last August. And so I come here in 2024. Okay, what do we remember that happened in 2024? Right? We had that big July 11th flood, and then that even bigger July 30th flood, and I got to be a whole part of that, and that really threw me into learning more about flooding, and especially the big thing that I care about, which is how can we keep people safe, especially in unprecedented times. And how can I learn more about this? Which led me to talking to you guys today, to looking at information and learning more so that I can help keep people safe, which is the ultimate goal here. So many of you know what the Eye in the Sky does. We produce our forecasts for you guys. It's okay. But not many of you know that we also do weather observations. We have the second longest history of observing the weather in the entire United States. Starting in 1894, we've had daily observations 3 times a day in the same exact spot using most of, if not the exact same instruments that they used to use. So we're one of the most succinct weather data sets in the nation, which is pretty awesome. This is what that station looks like out here behind the museum. This fancy, funny-looking white box is where we keep our temperature instruments, or thermometers. They measure our high temperatures, our low temperatures, and current temperature. And that white box just makes sure that our weather is accurate and it's not influenced by the sun or wind or anything like that. Then we have this funny guy here. This is our temperature and humidity sensor that we use. And then this guy over here with this crazy looking silver shield around it. This is our rain gauge that collects our rain and snow data. This fun fence here actually makes it more accurate. So if our rain is blowing sideways, it helps to cause the wind to be a lot lower, so it collects some more accurate rain information. So if it's blowing sideways, we're still able to catch it and measure it, which is pretty cool. And at the museum, here are our current conditions. Today's a little bit more exciting. It's above 40, so that's good. It's been a little while since it's been above 40, but this is where all of that information goes into that I can look at any time of day when I'm making a forecast. So it's really, really helpful for me to know exactly what's going on, even though I can look out the window and look at it, but this is also helpful. And then for the public, if you guys are ever interested in knowing exactly what it is in St. J at the museum, you can go to this place called aviationweather.gov. It's accessible for everyone on your phone or your computer at home. And if you zoom into Vermont, you'll see this guy here. This is the museum currently reporting. So if you're ever interested in what exactly is going on at St. J, you can pull it up wherever you are. And of course, you can zoom out and see the rest of the United States. Over here, I have rain or radar precipitation that's showing up just to show you what's to come soon that we're watching. Okay, so now we're going to get into the nitty-gritty of, well, what is weather and what is climate, since we're here to talk about climate today. Sometimes this can be a bit confusing, but weather is what's happening right now, at the minute, at the hour, at the day. Sometimes could be the month or maybe the season, but it's a shorter period of time. It's what determines whether or not you put on a jacket that morning or add a scarf. Versus the climate is an overall average. It means when you go out in August, you're not expecting to grab your down jacket and your hat because you know it's August and it's hopefully gonna be warm, and hopefully will stay that way. Same with winter, right? Most days you're not gonna automatically assume you're gonna put on shorts and a t-shirt to go outside. That's what climate kind of runs, is it helps to inform what your weather is going to be. And this is on the scale of years, decades, and centuries. And of course, one thing that we all remember is if you don't like the weather in New England, just wait a few minutes, right? This is showing you how fast things change if you're ever thinking about weather and climate. Remember, a minute later, it can be totally different, right, in New England. Okay, so now getting into climate change. It can seem kind of like a daunting task thinking about what it actually means. Now, there are differences between climate change and climate warming. Today, we're just talking about how things are changing and whether it's warming or cooling or in any direction. Climate has always been changing, and we're going to look at some of those changes. But the first changes that we're going to look at are changes in the average. So average temperatures, those seasonal changes. And the next part is the variability. So how often something happens, whether it's going to happen more or happen less, which is what we're definitely really interested in knowing about here, especially in the context of flooding, right? And these are over extended periods. Remember, climate is much longer. We're talking decades. In meteorology, we like to have at least 30 years to be considered a good period of climate. And this is just due to statistical reasons. You at least need 30 points of data for your data to be robust. So that's why we consider 30 years to be the prime. But in this case, we have a lot more than 30 years. We're very lucky. So we're actually going to look at beginning in 1900 and go all the way up to last December in 2025. Unfortunately, it is not possible right now to include data earlier than that due to limitations, but we're hoping if we get an intern or somebody up who can help us code, we'll include those other 6 years that are missing from this, but I promise they will be added in the future. Okay. So we're going to look in changes of averages, whether the number is larger or smaller than it used to be, variability, if it happens more or less, and over decades. So we're trying to remove those day-to-day differences, like a storm coming through or things like El Nino and La Nina, if you've heard those before. We're trying to remove those smaller trends to look at bigger ones over a longer period of time. Okay, so our average daily temperature helps us inform whether today's high temperature makes sense. So if our climate average in December is 20 degrees, I probably, if I'm forecasting, probably shouldn't put 40 or 50 degrees in the forecast. That would be way out of the norm. So it's informing those day-to-day weather decisions. But if these things change, if my average daily temperature has been increasing over the last 125 years, then I know today's high could be a little bit higher. And so this helps me make sure that my forecast is more accurate to help inform the public to be safe, right? So if the number of thunderstorms is going up on average, then probably there's more likely chance for a thunderstorm in the forecast. So that's how they kind of intertwine together. Now here's just an image of these records from 1984. If you're interested, when we're done with the talk, I actually brought a copy of the records with me. If you want to flip through them and look a little bit back in time, it's kind of interesting to see how they wrote down their observations. But you can see the maximum temperatures, minimum temperatures, average daily, the range in temperatures, and different remarks, whether it was clear or cloudy or things like that, which we still do it the same way, which is pretty cool. So before we look at daily temperature, it's helpful to know what this means. Our high temperature isn't necessarily the temperature at noon or 2 p.m. It's just the warmest temperature within 4 p.m. to 4 p.m. that day. So if that temperature happened at midnight, which sometimes it does, that's what the high is. Same with the low temperature. Sometimes when a cold front sweeps through, our low temperature isn't overnight, it's actually at 2 p.m. in the afternoon. So it doesn't matter when this happened, we're just taking the lowest of the low and the highest of the high. And then in this case, the average is you're taking those two, adding them together, and then dividing them. Here is our averages from 1894 to 2025. So this is just our average climate for St. J, just to give us a reference point of if we were to look at all 135 years here, what that would look like. And makes sense. January, right? We're in the middle here at, I don't know, 13 degrees with lows around 7 degrees and highs around 30. So this is just showing you an average over the course of each month, just to give us a reference point of kind of what we're looking at here in St. J. So I had the time to actually take in this data, organize it, and really get into the weeds and look at exactly how it's changing. And I'll walk through each of these with you. So each of these is every 5 years, but every year is a point on this graph. So you have years on the bottom where we start with 1900, going all the way up to 2025. Then on your y-axis here, we have our average annual temperature. So I looked at all of 1990, took every single day, every single observation, and averaged it into one number, which isn't super representative, but it gives us an idea, if we take all of that information, what number represents that year. And so we did that with every single year here, which is a total of 126 years, and I plotted it on this graph. And so remember to keep in mind of the scale here, each of these is a degree change. So even though the slope looks really, really big, it's not that big. But what I thought was really interesting is even if this line wasn't here and you looked at all of these dots, you can clearly see that they're changing. They're moving. If I looked at these dots back here and these dots up here, they wouldn't even really line up on the same graph. So this was a very clear indicator that things are changing. And one thing that's really interesting is that this is a very strong trend. It's about a 40% significant trend, which means that really warm and cool years aren't impacting this as much. It's very steadily going up. Then we can look at minimum, which has an even stronger trend, which is really interesting, that it's actually going up faster than averages. So this minimum could be what's driving that average temperature to move up more. So that's important to remember, is that highs and lows are averaged in the average temperature. And we can see this change over here. Now this scale, of course, had to be changed since minimums are a bit lower, from 25 to 40 degrees Fahrenheit, and still from 1900 to 2025. And very clear change happening here. This one has an even stronger trend of 50% significance. So this is definitely changing more and less to do with variance happening. And then for highs, these aren't changing quite as much, which was really interesting to find. When you think of climate change, you probably think of a lot warmer high temperatures, which they definitely are changing, but I thought it was interesting that they weren't changing as much as the low temperatures, which is something to look out for sure. And this ranges from 50 degrees to 60 degrees, and again, 1900 to 2025. And there's still this trend here. We have a few, outliers of really, really warm or really, really cold days, but overall, everything's going up. Now, this has a lesser significant trend of only about 25% significance. And so there's less happening with the highs, but we definitely want to look at our averages and lows. Those are really significant. And so if I put the change on average that's occurring over 126 years, the difference from 1900 to today in low temperatures is 4.5 degrees. So on average, today's low temperatures are 4.5 degrees warmer than they were back in 1900, which is a very big jump to think about. And we might not think too much about, basically 5 degrees, but that's the difference between a 70 and 75 degree day, which to me is very important when I'm trying to inform your forecast. Our average is about 3.5 degrees increase, and then highs 2.5. So you can see how our lows are increasing the most. Our averages are in the middle, but even our highs are still increasing, just not as significant. One thing to think about in our atmosphere is, what is it actually made up of? What is the stuff? What is the air that is warming up? Well, 78% of that is nitrogen, and 21% is oxygen. 0.96% is other gases. Other gases is really important. This is where our water vapor lives, is in kind of that other gas category, but it is in the air and, of course, runs our weather. And as our temperature increases, our molecules like to wiggle around more, and they have more energy. They're like a toddler. If you give them more and more candy, they're running around and bouncing off the walls more and more and more. And that's what's happening with our molecules in the atmosphere. So here we have a much colder environment, and as we get warmer and warmer, our air molecules start wiggling and running around a lot more. And so there's more energy in these molecules. You'll also see between them there is more space. There's more area, whereas down here they're much closer. If I'm trying to get in between all of these molecules, it's a lot harder for me to run in between them here than it is here. There's a lot more space. And also, because of this, the ratio of water vapor in the atmosphere goes down more and more and more the more your air heats up. So if you have the same amount of water and your space of where that water is growing, that's a less and less percentage. So for example, if I have an atmosphere that's 55 degrees and I want to fill it up halfway, that's what it would look like. But I would need more water to fill it up halfway if it's 75, and even more water to fill up if my atmosphere is at 95 degrees. So by adding 4.5 degrees, or even, let's say 4 degrees on average, this bin is getting bigger and bigger and bigger, which means there's more and more space for the water to go. And this is becoming a big problem, and one of the biggest points of research in weather right now is looking into exactly how much water is going to be added to the atmosphere because of this. Now, this is what our current precipitation looks like on average from 1894 to 2025. Precipitation is measured in inches, and our rain gauges, we actually go out and measure it by hand, and we'll stick our own rulers in there and measure our precipitation, which is pretty cool. One thing to note, that precipitation does include snow. It's just total water. We actually will go and melt the snow and then measure the water that was in the snow. So if you have a dense, heavy snow and melt that, there's going to be more water. If you have a really light, fluffy snow, you're only going to have a little bit of water. But we measure that water, and that's included in precipitation. So, similar. Total precipitation, this is from 1900 to 2025, measured in inches. Inches is on here from 20 inches to 60 inches. Now this is total by year. So over the course of the entire year, we added up how much rain there was and plotted it on this graph. And usually precipitation is measured in cumulative for the entire year. You add it up every single day to have one big total at the end. And that's what's plotted here across this graph. Now, it is kind of interesting that there are more kind of points that feel like they're spreading out towards the end. I mean, this could be because we have better accuracy now or for a few other reasons, but even despite this, there's still a clear increasing trend when looking at all these dots, and that makes sense because our temperatures are going up and there's more space for water, which is really, really cool to see that. Now, this trend isn't as strong, it's only about 20%, but we can still see that it is growing. Now, this is the number of days that it rains each year. So anytime we measured precipitation, or sorry, not just rain, also snow, anytime that we measure it, it counts as a day. So if it's sprinkled or downpoured, it doesn't matter. It rained that day, we count it. And this has one of the strongest trends out of all of them, which was really, really exciting, at least on my part, to see as a weather nerd. Here is the number of days starting at 100 and going to 200, and of course 1990 to 2025. And this has a 40% significance trend. So this is one of the strongest trends we saw overall. And this also has one of the biggest increases by year. It's not necessarily the amount of rain that we're seeing that is going up, but the number of days that it's raining is going up a lot more, which was really cool finding. So total annual precipitation on average compared to 1900 has gone up by almost 8.5 inches, but the number of days we have seen rain has gone up by 37.6 days, which is more than a month, which is crazy. Now, part of this could be the fact that we have better instruments that can measure things like small little sprinkles and stuff, so that could definitely increase this number for sure. And I think that's also why you're seeing those bigger spreads over time. But it doesn't explain all 40 days. So that's still very, very cool to see. And we'll talk about that a little bit more later. Okay, so now to snow, which was also really interesting to see. Here are averages from 1894 to 2025. Our biggest months are February and December, with January kind of having that lull, and then of course going down into the summer months, and of course the sneaky 5 inches there in May, which I'm not looking forward to. And so here's total annual snow in inches. This is from 1900 to 2025. Now, again, like precipitation, we're counting up all of the snow totals. So for 5 inches plus 5 inches plus 5 inches is a total of 15 inches that year. And this ranges from as low as 30 inches to as high as close to 140 inches. And you can see this has a pretty big spread in average values. There's less of a clear line of what to expect in Vermont, which is pretty cool to see. I could easily have 40 inches of snow one year and 135 inches the next. So this also definitely helps to inform a forecast, especially for thinking about like last year's snow season versus this year's snow season. Big difference, right? And this confirms that, which is pretty cool. This has very little trend and change at all. We're not seeing much in the way of changes. If I took away this line, you'd be like, what trend? There's nothing going on there, which is also really cool to know. No trend is also great information to have. So precipitation is going up, numbers of days of rain is going up, but total snow is not, which is interesting. Now, same with precipitation days. We counted how many days we had snow and looked at those. Not surprisingly, this has actually increased, but that makes sense since our total precipitation days are also increasing. It would make sense that snow would follow a similar trend here. Again, 1900 to 2025, we have 10 snow days all the way up to 80 snow days per year. And of course, each year is plotted here. This has a 30% significant trend, which is pretty good. And also has a pretty big increase. So precipitation days include snow days, and this trend definitely helps to reiterate what's going on. On average, our total annual snow has increased by about 8.5 inches, and the number of snow days has increased by 21 days. on average, which is pretty cool. Great findings, really interesting to see, which we'll talk a little bit more about why that is. So what I wanted to do was plot the first 30 years of data, right? Because 30 is the significant number that I need to really get a trend. So I looked at 1900 to December of 1929, so 30 years. Then I compared it to the most recent 30 years so that we could visually see if I had two climate graphs, what would change within them, what is changing the most. So this first one is plotting all three temperatures, right? We have our average temperature, our high temperature, and our low temperature. And this is by month. So from 1990 to 1929, this is what your temperatures will look like from January to December. And this is in Fahrenheit here, from 0 degrees to 100 degrees. And it looks pretty good. Above 80 in July for the high, around 0 in January for the low, right? Makes sense for Vermont. But I will click back and forth on these so you can see the difference. But here is 1996 to 2025. So this is also 30 years. And if I click back and forth, you can watch the graph wiggle, which is really helpful to see the differences. So this is 1990, 1929, and this is 1996 to 2025. So this is the same exact units, the same exact graph, but we're watching all of those wiggle up. So this informs my decisions to make forecasts significantly. I know that the weather has changed and I can expect my high temperatures to be quite a bit warmer. Now, this next graph, I know it's a little bit confusing, but stay with me. So what I did is I subtracted 2025, or 1996 to 2025, from 1900, 1930 to find the difference for each month and plotted it. So you could see visually which months had the most difference and which months had the most impact. So this is the change in temperature, not the actual temperature. So in January, your low temperature is 2 degrees warmer now than it was in 1990 across those 30 years. And your average temperature, almost 4 degrees warmer. And your low temperature, above 5 degrees warmer. And this is just for the month of January. And you can see how each month is a bit different. February's even more. So initially we were looking at averages over a whole year. This shows you variability by month and which months are impacted the most by this change. So for February, our low temperature has increased on average by 7 degrees, which is crazy. Yeah, very cool. I just found this out last week and I'm still buzzing about it and I'm so happy to tell everybody about it today. Very cool. What's interesting, I think, is that March, April, and May, all temperatures increased at the same rate at just about 2 degrees, which is interesting. Then if we go to July, our high temperature has actually gone down a little bit, which is pretty cool to see too. So this really helps kind of visualize how big those changes are per month. And then as we go into summer, right, our low temperature across the board has had the biggest change, which is kind of what we found. So I did kind of throw this table up here. This is the same exact what the graph was plotted at if you wanted to see the exact number for each month of which is changing the most. If that graph was a little bit not quite helpful for people who aren't as visual. So for January, change in average low temp was 5.3 degrees more, and then average temp 3.7 and 2.2. And I can also share this information with you if you want to kind of dive into it more and look more at these numbers. But the biggest thing is the changes in the winter months are the largest. That was kind of the biggest alarm bell to me. And does this quite make sense with how much snow we're having? I don't know. That's another thing to think about. So, of course, I did the same thing with precipitation. Here is 1900 to 1929, the first 30 years of data that we have, our first climatology. Again, your month at the bottom, and average precipitation in inches, 0 to 24. So from 1900 to 1929, I took all Januaries, their total precipitation, and then averaged it. So we got an average across the board. Blue is in snow, precipitation is, blue is snow, precipitation is green, which also does include snow. But we can see, of course, no snow in our summer months, which is good. Let's keep it that way. And then we can kind of jump back and forth like we did with the temperatures. So this is 1996 to 2025. This is the most recent 30 years. We can kind of do a hop back and forth. So this is 1900, 1995, 1900, 1995. So you can definitely see things are growing, which is really interesting. Now, we saw that there's more days that we're getting snow, and a lot more days we're just getting precipitation in general, which kind of makes sense based off of the fact that our temperatures are clearly going up and there's more availability for water. But then we can also do the little subtraction dance here too to see what months have the biggest change. So here, there's quite a few months that don't have that much change, especially in precipitation in green, kind of closer to 0. But for snow, there's kind of this big jump in March where we're getting more snow, which is kind of cool. And then we jump back down and are kind of losing snow in April and staying steady. We're dropping again in February and then shooting up in December where we're getting, more snow, which is kind of cool to see how things are changing by month. So we can put some numbers to that. I think the biggest things for snow is that in these kind of more transitional months of spring and fall, we're having less snow, which is really interesting. So this to me is telling me that if we're having less snow, temperatures are warmer during those months. Maybe our time that we're staying above freezing is just a little bit longer during the spring and the fall, or we're getting a little bit warmer faster in the spring, if that makes sense. So if it would have snowed, it's now turning into rain. That's what this is kind of indicating. Now there's still more that we can look at to really confirm this, but for now, I think that's a pretty cool initial analysis. Okay, so next thing everybody talks about in climate is extremes. We're talking about negative 25 degrees or it's 110. So that's what I wanted to look at. So I took the coldest day from each year and put it down here, put the coldest temperature ever recorded, plotted on the graph for each year. And it's going up, which some people might be happy about who don't like winter so much. Again, 1900 to 2025 here. And it goes from negative 45 degrees all the way up to a balmy negative 5 degrees for Vermont. Now, this doesn't have a huge confidence. It's about 20% confidence that explains the trend, so kind of on the lower end, but it still is steadily increasing. Now, this one kind of blew my mind. Maximum temperature. So I took the hottest temperature recorded from each year and plotted it. And it's not doing much, which I was kind of surprised about because we all hear about these much warmer extreme heat waves and things happening, which of course have humidity and stuff involved. But if we're just looking at temperature here, now this line, I just put it on here because this is what the line is, but there's less than 5% confidence in this trend. So this means that this trend is null. This trend isn't really a strong one or even one we can consider. 5% I would not count as anything statistically significant. So there's not much going on in absolute maximum temperature, which I was very surprised about, but also helps be very informed. Whereas minimum is definitely where we're seeing the biggest trends, which is, I think, very helpful. So our absolute annual minimum temperature has gone up on average by almost 10 degrees. So from -45 to -35. So don't get too excited. And annual maximum temperature is showing no significant change in that at all, which is pretty interesting result. So everybody's big question that they always like to ask is, so what does this mean for extreme precipitation? Now, this is a lovely gift from the National Weather Service of the radar on that fateful day where we got 8 inches of rain here in St. Johnsbury. We are right here. We can watch all that beautiful rain develop. And we know what happened after that. Just for visual effect, if you are interested in science or the exact impacts of this event, it's really helpful to, as me as a meteorologist, to go back and see this information so I can see how rivers actually responded to this much water. Since we don't have gauges, having somebody to take pictures and send us and do drone footage like this is really, really important. Since we only have one local gauge here that's down by 91, there's no way for me to know exactly what the impact is unless people go out and do their own citizen research like this. So we always appreciate if you see flooding, have flooding, ice jams, whatever it is, please take pictures, send them to us. It's really, really helpful for us to know exactly how people are going to be impacted by certain events. And so, of course, we looked at the biggest of the big rain events occurring from 1900 to 2025. And this is plotted in inches, so you can see lovely 2024 on the graph all the way up there. And there's no super clear trend in these extreme events going up, which is good. But I think it's important to remember that piece, at least piece of physics of the atmosphere, is where if it gets warmer, there's more room for water to move in. And so it doesn't necessarily mean that these are happening more, but I think it's important to remember that if it does happen, it's likely to be slightly worse than it would have been because we have added moisture or moisture availability in the atmosphere. So there's no way to be like, this specific storm was from climate change, but we can infer that more than likely it's a little bit worse, a little bit dialed up because of that. And this also shows that we've had strong rainstorms throughout the entire history here in Vermont. Of course, it does feel really recent in our brains, so it feels like it's happening every single year. But if we look at events that are 3 inches or more, which is what you usually need to have for really bad flash flooding, it's not happening super, super often, but it's definitely something to keep an eye on for sure. And so you can also look at, well, our number of days of rain are going up. Well, is each rainstorm getting bigger? Not really. This is showing how much rain occurred in each rainstorm on average across 1900 to 2025. You can see it's pretty steady. There's no real trend here going on that we're seeing, so we're not expecting individual storms to be much stronger. Again, that's still that little piece that could dial them up a little bit. But the main thing that we do know is that we're getting a lot more storms, a lot more rain happening more regularly, which of course means more flooding. But we are seeing extreme precipitation in the Northeast increase by 52% by 2099. If you're interested in this, I definitely recommend reading this recent study that was done by Dartmouth. They've done a lot of really cool simulations with climate and putting basically the information that I have found is similar to what Dartmouth has found with their data analyses, with more precipitation days going up and lower temperatures increasing more in New England. So this was very clear to me that at least the work that I'm doing is measurable by another institution. But if you're curious to see exactly with climate modeling what this could look like, I recommend looking into this. It's very cool. And so remember, more availability, we can have more water in the atmosphere. And there are a few different kinds of flooding that we have here in Vermont. The first one that we might think of is the flash flooding, which happened in 2024 with those 8 inches of rain. That's when we get a lot of rain all at once. It overwhelms our small rivers, and that's when we get those big landslides, and that's what's really dangerous. We're not quite seeing that signal right now for that to become much worse. The average availability of those extreme rainstorms seems to be staying pretty constant, but again, could be dialed up just a little bit because of this. But then we also have things like ice jams, right? We had flooding due to an ice jam just a few weeks ago. And that can definitely be impacted by these warming temperatures in the fall and the spring, where ice jams are more prevalent. But the biggest thing is if we're having more days of rain, the main way we get flooding out here is what we call river rises. So that's when you get multiple days of rain in a row, and by the third or second or even third day, that is when the river slowly encroaches its banks and slowly starts feeding into our roads. That's the big one. If we're seeing more days of rain, upwards of maybe even 30 days on average a year, the chance of having those days line up and those rivers overgoing their embankments is higher. So at least extreme flooding, we're not seeing too much there, but those slower, bankful moments are definitely happening, or not definitely happening, but are more likely to happen. And so, so the best thing that we can do, since we know that we're going to continue to get flooding in Vermont, that we're going to have these kind of more likely to get these slower rises where our typical areas usually flood along like the Linden Highway and typical farm areas, right? These are going to continue to flood and going to probably flood more often. But the good news is that these are the slower types of floods that we can evacuate people from. Whereas flash floods are, as you know, almost immediate and only have minutes to get people out. So it's good to know that if these are occurring, we have more time to evacuate people. So what I recommend is that since we know this is going to happen, have a flood safety plan, even if you don't live in a flood zone. Almost all of us have to drive through a flood zone to get home or to get to work. So knowing where those areas are, and if you hear flooding, just make sure to look those up. I always recommend New England 511 is a great resource. You can go online and see individual cameras of roads, so you can check out current conditions and make sure that your pathway to work is safe. Again, part of that is knowing your evacuation routes, where you can go. If you do live in an area that floods from these floods, make sure that you know which routes aren't flooded or which routes flood last, so you have more time to evacuate. Of course, listen to your local emergency managers. They're going to know these evacuation routes the best, and they're going to be able to help you the fastest. Our county emergency manager is Bradley Reed. He is the fire chief here. I work directly with him to help give up-to-date information when it floods or for fires or anything like that, or the ice jam, so that we can make sure that he has as much information as he needs to make the best decisions to keep people safe, which is pretty cool. Also, heed weather watches and warnings. I know it seems like the National Weather Service or even I put them out all the time, but we're putting them out when they need to be put out. I promise we're not trying to give you extra homework. We really just want to make sure that people know what's going on so that they can be safe. And if you see something like a flood watch or a flood warning, I just recommend just looking into it a little bit, making sure to see who's impacted and where, so that you can have or enact your flood safety plan. And of course, in Vermont, the number one thing we can do is support one another. We all saw this last summer. We came together. We helped to, dig out debris, support each other, find resources for each other. This is going to be the biggest one as we get more floods or even more precipitation, just being there to be each other's resource, help pick each other up, and especially you all being here, knowing this information, sharing it with other people so that they can also be informed and know how to be better prepared for the future, for sure. That's it. you have any questions. Yeah.
With all of this increased moisture, how do you explain the drought that Vermont was experiencing last year?
100%.
It's different places, but...
That is an amazing question. Yeah. Climate informs weather, but is not always to a T, right? We have our averages of what we can averagely expect over the summer, but sometimes that doesn't exactly happen. We're not always having an average summer. So this past summer was definitely not an average summer. We ended up having a weather pattern that kept on missing us. So precipitation kept on going around us where typically would go over us. And so those are those seasonal variability and shifts that can happen year to year. And that's when you can get extremes. And just because extremes happen, like drought, doesn't necessarily mean that the overall changes are happening at the same time. Both can be completely true. On average, we're going to continue to experience occasional periods of drought and occasional periods of a lot of rain, but that's just well within Vermont's variability. Just means maybe the drought wasn't quite as bad as it would have been. If that answers your question. Yeah.
Well, the Arctic is a bit of a wild card with its weather, and I was just wondering, because I know the Arctic is actually warming the fastest out of anywhere, I guess, on the planet, and I was wondering how the weather there will affect, what it's doing up there will affect Vermont because we're so close to Canada.
Right. This is also one of the main reasons why places like New England are warming the most in the winter months, is because we're up further higher on the latitude lines. And it makes it easier for change to happen because we're not as close to the equator. The equator is pretty steadily warm, and the further away you get from that, the more variability there are in temperatures. And same with the Arctic, the further you go up, the more likely, or the more wiggle room there is for temperatures to change, since they're not getting that constant sun heating like places like the equator are. And so that's also especially why we're seeing the biggest changes in December. Now, as the Arctic changes, that will support changes in our jet stream and where it's located. Our jet stream, of course, are the fast-moving winds that go all across the world, and they're made because of the difference in temperature at the poles and the equator, and where those winds meet, or where those temperatures meet, makes the wind the strongest. So that's why we have a jet stream. But if our Arctic is changing the fastest and getting warmer and warmer, that's going to change where those differences occur and where the fastest wind speeds occur. And so having the Arctic warm more could shift which storms we're getting, which could be why we have more days of precipitation, because the Arctic could be shifting us in a position where we're getting hit by the jet stream and hitting more and more storms, which is definitely a future point of research for sure, which I know a few universities are looking at.
Right, thanks.
Yeah, sorry if that made sense. Did a whole loop around there, yeah.
Yeah, is it true that the jet stream seems to be going south more than it used to?
Yeah.
Even taking cold air down there, and goes down there and picks up warm Gulf saturated air, brings it right up the East Coast.
Right. That is a great question. This is back a few years ago. I talked with a few researchers who were specifically studying this topic. Research moves really fast in the weather world, so I could be a few years old here, so definitely look at more recent research. But when they were doing that, their biggest findings were that because of the changing temperatures, the jet stream wasn't as strong, which allowed it to kind of wiggle around a lot more because it wasn't as available, like it wasn't, the difference in temperature wasn't strong enough to keep it where it was. Because it was a little bit weaker, it allows it to kind of wiggle a lot more, which is causing it to dip down. I haven't heard specifically, and some of my colleagues here can probably give more information about it, if it's totally shifting down, but I have heard that it is more variable. So it's moving down more often and moving up more often, which is kind of why we also get these really cold outbreaks. So climate change can make things colder too. I hope that answers your question.
Thank you.
Yeah.
A couple of really small practical questions about forecasting. Why is it 4 p.m. to 4 p.m.? So what am I looking at when it says the high today is going to be?
Great. That's a great question. In the meteorology world, we have to make a cutoff somewhere so that everybody's data is the same. So that when I'm looking at high temperatures here and I look at high temperatures in Alaska, I know that they're the same time period. So it's kind of just what meteorologists use. Now, when you're talking about highs during the day, and if you're looking at like your phone app, for example, they're doing it during that sun up to sundown period. Which again could be lower in the afternoon if you have that cold front moving through, of course, but for practical reasons, for the general public, it's just sun up to sundown when the highest temperature would be. And again, that could be later or earlier depending on if weather's moving through.
The other one was just, again, you had a lot of information about precipitation versus snow, and I wonder how that's collected when there's a changeover and how you're being accurate about how much precipitation is snow and how much is rain.
Great.
When things are changing.
That's a great question. We are fortunate enough that we have instruments that record every hour that can tell us when we're asleep, give us a better idea. Now, unfortunately, we're not the National Weather Service. We don't have a night shift. We just have a morning and a day shift. So there can be some discrepancies, of course, overnight. Like this past weekend when we got snow, it was really heavy and wet. I did my first observation, or my last of the day observation at 4 p.m. Then I, went home, slept, it snowed more, and then I got up in the morning and I measured that snow first thing at 7 a.m. But again, because it had sat overnight, it definitely shrunk. And there's no way for me to know exactly how much it shrunk. So I measured 0.9, that's what was measured during the day, but it could have been 1.5 inches when it first fell. So there's definitely discrepancies a little bit there for sure. But another thing that helps is collecting water. The amount of water you collect doesn't really change. And so I can go melt that water at 7 a.m. I know how much water melted. I know roughly the ratio between water and snow because of my last observation. So I can kind of adjust. So if I had fluffy snow and I had 0.02 inches of rain and 2 inches of snow, I could adjust for that afterwards because my water isn't gonna change, if that helps. But yeah, there are small things like that for sure.
Thanks.
Yeah. Anything else? Cool. Well, thank you everybody for coming out. I really appreciate it.